an idea where we can look at the Merton portfolio optimization problem, but where we're going to let the utility function depend both on the consumption and time. And we're not going to work with the case where we worked with the Cara utility, so there's no longer going to be constant relative risk aversion. Okay, so we're going to consider a kind of more general objective function. Okay, and I want to show how we can still come up with solutions, albeit perhaps we need to be finding those solutions numerically, but we can still find solutions to this HJB equation. Okay, so now we're going to have a utility function. So in that integral for the Merton portfolio optimization problem, rather than having u of c, and u of c being a Cara utility, okay, or rather than having more to the point, let me write it here, so rather than having e to the minus rho of t u of c, okay, where u of c was generally a Cara utility, we're going to replace it with u of t of c, okay? So we're going to put in a slightly different utility function in, okay? And the things that I'm going to assume about that utility function are that it's continuous in t and c, and it's also going to be concave in c, all right? And I'm going to assume it's concave in a way that it's sort of increasing, and there's a limit equal to 0 of the derivative of the utility function. So that's just a sort of bunch of assumptions that make things sort of reasonably safe, but still general, considerably more general than Cara utilities. Okay. Now, so I can write down the the HJB equation for this problem, and now I'm going to be dealing with it where I'm going to be looking at v of t of w. Okay. So that is the optimal objective function for the Merton problem, but where I start from time t with wealth w. All right. So before we were just dealing with v of w, and that's because we know as we let time go forward, we only have to just multiply by a discount factor. Okay. So notice previously v of t of w was just equal to e to the minus rho of t of v of w. Okay. So we could work with just v of w rather than v of t of w. Okay, so now things have changed a little bit. We're working with this function instead for the value function, which is the solution to the Merton portfolio optimization started from time t, and that's because we've now let our utility function depend on t. Okay, so because the various parameters of the problem are now dependent on t, in particular the instantaneous reward we get from consumption is allowed to depend on time, we have to let our value function depend on time. Okay, now, okay, so that's going to slightly change our Merton problem. The main change is that rather than having a term that is sort of minus rho of v, we replace it by the partial derivative of time. Okay, so notice if I differentiated this with respect to t, I'd end up with sort of minus rho times this function. Okay, so that's where that would have normally come from. So there's a slight change. But the logic remains the same. We have the instantaneous utility, okay? Then we have something that accounts by discount, partial derivative of t, v with respect to t, okay? That's where our normal discount factor would be. And then the drift term that I would get from Ito's formula, okay? So the form is essentially the same as before, instantaneous cost, rate of discount, and then the drift term from Ito's formula. Okay. Notice this would also be the drift I'd get from Ito's formula for the function v of t of wt. If I looked at Ito's formula, I'd pick up this extra term for the partial derivative with respect to t. Okay. All right. So enough about that. Let's now just take this HJB equation as given. Okay. So this is the HJB equation that we're dealing with. Okay. For this type of problem. Now, can we go about solving it? Okay, and the point of this is to show that we can take something that's actually quite a complicated formula here. So notice we've got a partial differential equation here, okay, with second order derivatives and everything, and with maximizations over the sets of portfolios and over the consumptions. Okay, so it's a bit of a mess of an equation, all right? And the point of this dual value function approach is to essentially apply a sort of transform to this equation, okay, which will then simplify it, and we'll see that we can actually reduce this rather complicated partial differential equation with maxima and minima in it, okay, into something that is just a normal ordinary differential equation, okay? And so, you know, the idea of applying transforms to partial differential equations isn't a new idea, so you get used to sort of Laplace transforms, Fourier transforms, okay? And this one we're going to apply something called the Legendre-Fenchel transform, okay? So the idea here is we're going to define some new function u of star of z, okay, which is going to be the maximum, okay, of u of t of c minus z of c, okay? All right, and notice we've already got something of that form inside this expression. If I look at the maximization over c, I've got u of t of c minus c times this, the partial derivative of v with respect to w, okay? And so if to maximize this, the maximum is going to occur, all right, where we take z equal to the partial derivative of v of w, and the derivative of this has to be equal to that, okay? Now, if I looked at the same thing with my objective function, v of t of w, okay, I could also do the same maximization. I'd end up with a function j of t of z, okay, where z is equal to the partial derivative of v with respect to w as well, okay? So I could do something very similar here, okay, and when I'd solve for maximization over w, okay, w would have to relate to z through this expression here, okay? Anyway, so basically what we're just doing is defining two new functions, u star and j, all right? Where j is given by this, and z relates to w through this expression, okay? And now, what we can show, okay, as I showed in the class before, is the following expressions, okay? That the partial derivative of j with respect to c is equal to minus w, where w relates according to this expression. Then we have another expression for the second partial derivative of j, and for the partial derivative of j with respect to time. And in each of these cases, I end up with a relationship to the derivatives with respect to v, the kinds of things that I care about in this expression here. Okay, so I'll show the first derivative here, and I'll let you figure out how the other two work. It's not too hard. Okay. As I mentioned in class, there's a bit of a deeper theory here of Legendre-Fenchel transforms and how they work with derivatives and inverting derivatives. Okay, I'm probably not going to go into that too much, but I just want to show sort of through standard calculus techniques how these results hold. Okay, so let's first just ignore, if we're just going to show this result here. Notice it doesn't really depend on time, so I'm just going to ignore the time component of j. So I'm just going to say that we've got j of z, okay, and then from this expression, okay, I can see that this, if I let v be my function, I'm basically differentiating v, okay, so I've got z equals v of w differentiated, okay, so that implies that w is equal to v dash to the minus 1 of z. Okay, now let's substitute all of these parts in. Okay, so now I am looking at j of z, which is equal to v to the minus 1 of z, okay, minus z v to the minus 1 of z. Okay, so they're just this expression here with this substituted in for w. Okay, and now we want to differentiate this with respect to z. Okay, so the derivative of this with respect to z, well, oh, and I should have a dash on these, sorry, so it's a inverse of the derivative, apologies. So I want to differentiate this, and I can use my usual rules of differentiation here. Okay, so I would differentiate this, bring this outside, and then differentiate the term outside. So normal chain rule. Okay, so chain rule on that term would give me dv dash to the minus 1 of z dz times the derivative of this guy, v dash times v dash to the minus 1 of z. Okay, so that's chain rule applied to this. Now let's differentiate this guy, and I can use sort of product rule. Okay, so I can differentiate, say, this term, and then I'll differentiate with respect to z. Okay, so I'm going to end up with minus z, the derivative of this guy. Okay. Okay, and then I can differentiate with respect to z, and I'm going to get minus, and the derivative for z with respect to z is 1, so get v dashed to minus 1 of z. Okay, another thing to notice is that we've got the derivative of v applied to the inverse of the derivative of phi, okay, which is just going to give me the identity function. Okay, so I've applied a function to its inverse, and so I'm just going to get back to where I started from. Okay, and then notice that we've got this strange derivative times z in both expressions here. We've subtracted them off each other, so this is going to cancel with this, right? And so all I'm left with is minus v dashed to the minus 1z, which I can see from this expression is just w. All right, so all this is just w. Okay. All right. Okay, and then from this we can apply similar calculus rules to derive this guy. Notice I'm going to take the derivative of this with respect to z a further time, which is going to give me that. Okay, and also the partial derivative with respect to time is just going to follow by normal calculus rules. Okay, and you can look at these on the notes on the web. Okay, to see how those calculations go. All right. Anyway, so I've got essentially a bunch of relationships between the various partial derivatives in here and the partial derivatives of this function jt of z. Okay, so now we can essentially look at those and notice that I can remove, okay, all of the maximas and minima in the original HJB equation and just replace them with partial derivatives of this function j. Okay, so it gets rid of one sort of bit of complication in that expression, these maximizations and minimizations. Okay. So let's do that quickly. So, so notice I can write down the HJB equation from above. Okay, so I'm just looking at this. Oh, sorry, went too fast. Sorry. I can write down this HJB equation again. Okay, and I'm going to collect the terms that do with theta and the terms that do with c. Okay, so that's going to give me. So that HJB equation up there is exactly this. Okay, so just writing this out. So the terms to do with c, the terms to do with theta, then the terms that have nothing to do with theta or c. Okay. All right. And I can notice, all right, that I have got that this is equal to u star of t of z. Okay. Oh, sorry, u star t of the partial derivative of. I'm noticing I've got some typos here, so sorry. This guy should be C, and this guy here should be Z. Okay, good. Okay, so if I look at this expression here, I should have u star t partial derivative of v of w, which is equal to z. Okay, right, so that's the first term here. All right, and then I can apply my previous lemma that we proved in the last section about what the maximum of this is. Okay, so remember that this guy is equal to minus a half kappa squared, okay, partial derivative of v squared divided by the second order partial derivative of v. Okay, from our previous exercise on where we had multiple assets in portfolio optimization. Okay. All right. So now I've got something that doesn't have any maximizations in it. All right. And then I can substitute in the values of the j's. Okay. So, for example, this guy is going to be the partial derivative with respect to t of j. Okay. By this term here. All right. For this term here, I'm going to get the second order partial derivative of j. Okay. For this term here, that's just equal to z squared. Right. This term we've dealt with. This w, remember, is equal to the partial derivative of j with respect to z. Okay. And then finally, v, okay, oh, sorry, I've got a typo in here, that should be partial derivative. This is going to be equal to z, okay? So I say substitute in all the values related to j. This change of variables is going to give me, okay, so a z squared from that guy, the second order partial derivative of j from this guy with the minus sign applied. For this guy, I'm going to get a plus partial derivative with respect to t of j, and for this guy, I'm going to get r, assuming I probably made a sign mistake here, so let me just put minus signs right here, so I think that one needs some minus here, okay, I'm going to get minus rz partial derivative of j with respect to c, okay, which is what's here, okay, right. So essentially just work out the maxima in here and then make the substitutions for j. Alright? So now we've got a PDE which we could solve numerically without these maxima in it. Okay, and find out what j is. And then from j we can work out what the value function v is. Okay? Right. So now suppose that we can go a little bit further than this and simplify this partial differential equation to an ordinary differential equation. Okay? This is going to work in the case where I assume a specific form of the utility function, ut of x, I'm going to assume has a discount factor, like before. We're going to have u of x or u of c being a concave increasing utility function. Okay? And like just as before, okay, as we did in the previous exercise, we can show that the relationship between vt of w is e to the minus rho t of vw. Okay, and I won't go through that again, but we've done that previously when we first introduced the Merton problem. Okay. An additional thing we can say is we can now look at j of z. Okay, and j of z is going to relate to capital J of t of z. Okay, with this formula here. So it's going to essentially apply the same. It's going to apply the same e to the minus rho of t term. Okay. So we've defined j of z to be v of w minus wz, where again we have that z relates to w in the same way as previously. Then we can then look at the partial derivatives, okay, of capital J and relate them to the normal derivatives of j. Okay, so and I'm going to kind of leave it to you to do those calculations, all of them fairly straightforward, okay? So it's just a matter of, okay, so first of all you can check this one by just multiplying both sides by e to the minus rho of t, and I'll end up with exactly the expression that I got for the maximization of v of t of w minus w of z with an e to the minus rho applied, which is going to give this y here, okay? And then, given this expression holds, we can derive all the other parts, okay? So if I take the partial derivative with this respect to z, okay, that's the same as differentiating this guy with respect to z, and there's a relationship between z and y. We can see why this expression holds. And similarly for the partial derivative with respect to time and the second order partial derivatives, okay? Right, so I'll leave that to you to do the calculation for. So the first bit is just check this expression, and then the rest of it just kind of follows. Right? Now the main thing that we get from this is we can look at our previous expression, which was to do with the partial derivatives of capital J, okay, and get this normal ordinary differential equation, a second order differential equation, okay. So let's just look at that now. So show that the HJB equation becomes this. Okay, so let's do the answer for that. All right. So the differential equation that we had before, the PDE that we had before, was this. Okay. And now we can look at each of these terms, okay? So we can check that this guy is just e to the minus rho t times the Legendre-Fenchel transform of the utility function z, okay? And here I can substitute in the partial derivatives from above, here, okay? So in particular, I'm going to end up with this being equal to minus rho e to the minus rho of t j of y plus rho e to the minus rho of t y j of y. Oh, sorry. Yeah. Y j of y dash, the derivative of that. I can also substitute in for this guy from the expressions above. This is going to give me e to the minus rho of t y j dash of y. Okay. And then from this guy here, I'm going to get the sort of second partial derivatives for j, which are up here. Okay. And this is going to give me a half kappa squared y squared e to the minus rho of t, second derivatives of j. Okay. When I collect all these terms together, you can notice it's just this expression times e to the minus rho of t. Okay. So applying all the substitutions from the differentiation above, you can notice now I've got an expression which relates to the Legendre-Fenchel transform of the utility function that we're working with. Okay. And then some function y that we need to solve for. Okay. And this is a kind of quite a nice ordinary differential equation with second order, okay, and from sort of standard ODE theory, which I'm not going to go into, this has a solution of this form, okay, that y is essentially power function, okay, so we need a particular solution for this term, and then the kind of homogeneous solution part here, okay, is going to be a power function, okay, to deal with these kind of y's here, okay. And we can show that the roots of those are the solution to this equation. Right? So in principle, at this stage, you could solve numerically for this term, have the particular and A and B, okay. Once you've got the numerical solutions for the little j's, you can then calculate what capital J is, and then from capital J, we know how that relates to the function v. Okay, so we can essentially invert back to get v, right? So essentially, we can show that if we wanted to solve the Merton portfolio optimization problem for a general utility function, okay, or reasonably general utility function, okay, let's say of this form, then it comes down to solving this ordinary differential equation, okay? We might need to do some numerics to do that solution, but in principle we can solve a much more general form than the carry utility functions. That said, carry utility functions are quite a good special case to work with because they're all the cases where your attitude towards risk is multiplicative. So if you double your wealth, you're willing to invest twice as much money. Okay? Alright. Okay, so that gives a kind of overview of some of the basic ideas of solving these Merton portfolio optimization problems. When we come back after the Easter break, we'll look at some generalizations of this and some examples where we can apply this framework to a lot of different financial settings. Okay? Right. Okay. That'll do for now. Thanks.